All right, so let's look at second order differential equation. Okay. First things first, let's take a definition. Okay. A second order differential equation is simply a differential equation of the form d squared y all over dx squared plus a dy dx plus by, it's equal to 0. All right, so this is a second order, or this is the order or the form of a second order differential equation. All right, so when you see a differential equation of this form, you know that it's a second order differential equation. Now, from our previous class on calculus, we knew that dy dx can also be written as what there, y prime, and also the squared y over dx squared can also be written as what there, y prime prime. So if I bring this idea here, that means a second order differential equation can still be written as y prime prime, that's this, plus a into y prime plus by, it's equal to 0, where a and b are arbitrary constants, please. A and b are arbitrary constants. So basically, this is the concept of, or the form of a second order differential equation. We have this. All right, proceeding from here, let's look at the steps to solving questions on second order differential equation. Now, here's an overview about second order differential equation. If you can solve quadratic equation, you can do second order differential equation. So basically, the key to solving second order differential equation is just simply knowing quadratic equation. That's all. All right, as crazy as that sounds, it's true. Now let's see. Let's look at some steps. Let's look at some steps involved. What are the steps? I'll give you 3 steps to solving literally any second order differential equation. Just 3 steps. All right. Step one is that put y as equal to exponential mx. Right. You find the first derivative and also the second derivative. For this, the first derivative is given by y prime, also called dy dx. Now, what's the value of y prime for this? We know fully well that when it comes to differentiating exponential function, the task is simple. What's the task there? We said differentiate the power. Whatever thing you have, do what there? Attach to the question. So the power here is mx. If I have mx, if I differentiate mx, what do you get there? You get what there? M. Now attach m to this. It becomes what there? M exponential mx. So that's your first derivative. Let's get the second derivative, y prime prime. For y prime prime, let's differentiate this. Of course, this is a constant. Keep it pending. Come back here. I'm having exponential mx, this. Let's differentiate this. Of course, to differentiate an exponential function, as we said earlier, differentiate the power. If I differentiate mx, what do I get? If I differentiate mx with respect to x, what do I get there? M. Attach m to this, becomes m exponential mx. In essence, if I have to differentiate m exponential mx, the concept is this. Keep m out of this, which is m. Now differentiate exponential mx. You have m exponential mx. Now combine everything. Multiply this and this. What do you have there? M squared exponential mx. That's all. All right, so y equal to exponential mx, y prime, that's the y dx, is m exponential mx. Then the squared y over the x squared, which is y prime prime, is equal to m squared mx. Y prime is m exponential mx. Y prime prime is m squared exponential mx. Let's proceed. That's step one. Step two. Step two. Step 2, I will substitute the value of y prime and y prime prime into the given second order differential equation. Substitute the value of y prime and y prime prime into the given second order differential equation. You have that's step 2. Then when you're done with this, after this, from this, the next thing you have to do is factorize exponential mx and get the quadratic auxiliary equation. All right. So when you're done with substituting, you'd have to give you a particular equation. If you factorize exponential mx from it, you have what is called a quadratic auxiliary equation. That's step 2. Final step, step 3. Solve the quadratic equation. Solve the quadratic equation to get the two linearly independent solutions and the general solution. All right. To solve the quadratic equation to get the two linearly independent solution and the general solution. That's about it. Let me throw some emphasis on this. We said 2. All right. Why is it 2? Well, we know that if I solve a quadratic equation, how many answers do I expect? 2. That's why we say 2 linearly independent solutions. So in solving second order, you have 2 types of answers. The first answer you'd have is what is called the linearly independent solution. The second answer is what is called the general solution. Right? It's from the linearly independent solution that you get your general solution. Now that's one. Number 2, the value of the linearly independent solution is depending on the type of root of your quadratic equation. By type of root, I mean the answer of your quadratic equation. Cast your mind back then when you learned about quadratic equation. We said a quadratic equation will give you how many kinds of answers? What are the types of roots of the quadratic equation? What are the types of roots? For a quadratic equation, when you solve a quadratic equation, you expect how many kinds of answers? You expect 2 answers, but how many types of roots do you have? You have 3 types of roots of a quadratic equation. 3 types of roots. The first type of root is called what there? Equal. Sorry, let's start with real. Real, also called distinct roots. The second one is called equal or coincidental roots. Please check back on the class on quadratic equation. Equal or coincidental roots. The third one is called the complex or imaginary. All right, the these are the three types of roots of a quadratic equation. Now, again, as I said, the answer you get as regards the linearly independent solution is depending on which kind of root you get. If I have a real or distinct root, what will the two linearly independent solution look like? If I have an equal or coincidental root, what would it look like? If I have a complex root, what will it look like? Let's take them one after the other. By the time you get this one, by the time you understand this thing, you've gotten third order, you've gotten nth order. Both nth order, third order, and second order are the same concept. So why second order will give you a quadratic equation? Third order will give you what there? A cubic equation. Same thing. So you now see, say that this thing that you learned in year one, you've forgotten already. This thing that you learned in year one is now a sub under this. But now you now go to year three. This thing you're learning here as a topic will now be a sub under something. Go still solve. Do you have calculus calculator there? At this point, they don't expect you to solve quadratic in full. No, they don't expect you. All right, let's proceed. All right, so let's proceed. Going back to recall the types of roots of a quadratic equation, we said the first kind of root you have there is called the real, also called distinct. Distinct means they are not the same. Distinct means they are not the same. They are different. Now, we said let's look at this. Let's m1 and m2 be the roots of a quadratic equation. Let m1 and m2 be the roots of a quadratic equation. For them to be real or distinct, they should not be the same. In other words, m1 is not equal to m2. They are different. So m1 could be 3, m2 is 7. They are different. In a case where they are different, what will the in a case where they are different, what will the linearly independent solution when they are different, the linearly independent solution will be given by there's this thing that happens whenever you know you're wrong. The linearly independent solution will be given by you have two of them. The first one is y1, and y1 is equal to exponential m1x. Now, by m1x, we are saying the function is in terms of x, and y2 will be equal to exponential m2x. You have this. So if I have two distinct roots, you have that the linearly independent solutions is y1 equal to exponential m1x, and y2 is equal to exponential m2x. That's this. This is done with the idea that you have a dy dx function. That means I am differentiating with respect to x. So this is the linearly independent solution. The general solution is given by this. It's given by y. Let's say a function in terms of x, y of x is equal to, you have c1 y1 is C1 y1. What's the value of y1? Exponential m1 x plus c2 y2. What's y2 there? Exponential m2x. So you have this. So this is the first you have. All right. So this is what you have for general solution. Let's look at the second one there. Second one there is equal. What if it's an equal root? What do you have equal? We said equal is also called coincident or coincidental. What something is coincidental? It means that what they're the same. Coincidental roots. For equal or coincidental roots, what do you have? For this, we are saying that M1 here is equal to what there? M2. They are coincidental, they are equal. So in this case, what happens? You have that the linearly independent solution is given by y1 being equal to exponential m1x and y2 is equal to exponential m2x. So you have this. So this value of y1 and y2, basically you have this. What about general solution? The general solution, so if you look at this, the same thing as the first one here. Basically, the same thing. Y1 this, y2 this, the same thing, basically. The general solution will be given by what? Be given by y. Let's say a function in terms of x, yx is equal to what you have here. It's c1 y1, which is exponential m1x plus. Now here I have c2 this, but in coincidental root it would be plus c2 then x and then exponential m2x. So if you look at it critically, both real and equal roots are very similar. The distinction is adding x to c2, that's all. The distinction is adding x to c2. All right, that's it. So this is what you get. The third one, number 3, let's look at imaginary, complex, or imaginary roots. For complex or imaginary roots, we have that, of course, in this case, the value of the roots of the quadratic equation are now complex numbers. How does a complex number looks like? We'll have that m1 is equal to a complex number in year 1, when you did your year 1 maths, has two types of answers. What and what? Two parts. The real part and what the imaginary part. You have this as a plus ib, then the m2, the second answer would be what there? A minus ib, or bi, as the case may be. Right? Real part, imaginary part. So if I solve the quadratic equation and I now get imaginary answers or complex roots, what do I do? Note that the linearly independent solution would be this, that y1 is equal to, for this you have exponential ax cosine bx, y2 will be given by exponential ax then sine of bx. You have this. These are the two linearly independent solutions. What about general solution? The general solution, the general solution will be given by, let's say, a function y in terms of x. For all of this, we are assuming y or a function in terms of x. For this one here to be C1, then exponential AX cos BX plus C2 into exponential AX sine BX. So you have this. All right, guys. So once you get these stuffs in your fingertips, you can solve literally any question on second order differential equations. Right. So these are the things you need to note to be able to solve questions as regards second order differential equations. Let's take some examples and see how we can apply these concepts in solving second order differential equation. All right, all right. So look up, look up, look up, look up. Let's look at this, please. Let's look at the first example on second order differential equation. So look up, please. The question here says, find the solution to the differential equation, this one here. Now, they might not tell you find the solution to the second order differential equation. No, they'll say to the differential equation. So using your eyes, you can say that this one here, based on the fact that the highest differential coefficient is the squared y over dx squared. We can say it's what there? The second order differential equation. So here is the second order differential equation. The first thing you want to note is that the coefficient of the squared y over dx squared is unity. That means it's 1. You can now proceed to solve. For this one here, the coefficient is already unity, so we don't have to stress. Now let's solve this. How do we solve this? Step 1. What's step 1 there? Put y to be equal to what there? Exponential mx. All right. So step 1 would say let y be equal to exponential mx. We said find the value of what there? Y prime and what there? Y prime prime. What we said y prime is same thing as what there? Dy dx. So find dy dx. From here, what's dy dx? Dy dx is equal to what there? M exponential mx, as we said earlier, and y prime prime, the squared y over dx squared is equal to, what do you have here? M squared exponential mx. So you have this. This is always your first task. Y equal to exponential mx. You find the y dx, find the squared y dx squared. That's step 1. Step 2, substituting. Okay, so substituting. If I substitute, what do I get? In place of this, what do you put there? M squared exponential mx. So this one here becomes m squared exponential mx. That's this minus, so minus 6 into what there? Dy dx. What's dy dx there? M exponential mx minus 16 into y. What's y there? Exponential mx. This is equal to what there? 0. That's what step 1. Do your substitution. Let's expand this. If I expand this, what do I have there? This gives me m squared exponential mx minus 6, this one here, 6m exponential mx minus this and this 16 exponential mx. This is equal to what there? 0. I have this. So that's task 1. After this, what was the next thing we said? Factorize what there? Exponential mx. So let's factorize exponential mx. So basically, task is this. Take out exponential mx from here, here, and here. If I take that out, I'm left with what here? M squared. So m squared here minus 6m here minus 16, please. Okay. All right. Minus 16. This all multiplied by what there? exponential mx, it's equal to 0. So I have this. Basically, I have now factorized this. Of course, in this case here, this is what we call the what auxiliary equation. What I said, when you factorize it, you have what there? An auxiliary quadratic equation. This is the auxiliary quadratic equation.